Hello, welcome to AP Physics at Lyons Township High School. Today we have an example involving impulse and momentum, and the vast majority of it is conceptual. There is one calculation at the end, but it's in variable form, so you will not need a calculator for this one. So what we've got here is we've got a little super bouncy ball colliding with a large, let's say, beach ball. And we're going to assume that the collision is perfectly elastic. And I have a whole series of questions, and so I'll move over. You might want to write them down, and then there's actually two more in the next board. So I'll move over. You may want to write them down, okay? So go ahead and write those down. All right, now we're going to ask these questions, and then we'll go through them one at a time. The last two questions are right here. So again, you may want to pause the video and write those down. All right, so little ball hits big ball, okay? And they bounce off each other. Little ball's moving and the V-naught, big ball's stationary. So it's like you're throwing a little bouncy ball at a beach ball. And we're asking what happens. And we're going to assume that the mass of the beach ball is much, much bigger than the mass of the bouncy ball, okay? So first question, which ball experiences the larger force? All right, well, that should be an easy one to answer, okay? If A hits B, B hits A with the same amount of force and in the opposite direction. The forces acting on the two balls are the same. The force on, we'll call this ball A, we'll call this ball B. The force of A on B has to equal the force of B on A. We know whose law that is, Newton's third law, and it's always true, okay? So it doesn't matter which ball's bigger, it doesn't matter what kind of collision it is, none of that matters. If A hits B, B hits A, same amount of force, opposite direction, okay? So for number one, the answer is they're the same. They feel the same force. Number two, which ball experiences the larger impulse? Well, impulse is force times time, okay? We just said they both experience the same force, and you have to make the assumption that if A is hitting B for some time, let's say a quarter second, then B is hitting A for a quarter second. They're in contact together for a quarter second. So if their force is the same and their time the same, the impulse on each ball must be the same. So the answer to number two is same. Number three, which ball experiences the larger change in momentum? Well, a common misconception here is to say the little ball experiences a bigger change in momentum because it moves more, this motion changes more. Well, that's not true, okay? Impulse is change in momentum. We just got done showing that the impulse on both balls is the same. So the change in momentum of both balls has to be the same. Question four is where we finally get a different answer, okay? Which ball experiences the larger change in velocity? Well, momentum, or in this case, change in momentum, is equal to m change in velocity, all right? Well, they both have the same change in momentum. The smaller mass is going to have the larger change in velocity, and vice versa. The larger mass will have the smaller change in velocity. So the ball that has the larger change in velocity is the little dude. We're going to show in a little bit that his final velocity is to the left at about v0. The big dude moves off very slowly, okay? Number six is momentum of the little ball conserved. Well, the Pavlovian response is, oh, yeah, momentum's always conserved, momentum's always conserved. Well, it depends on your system, okay? Momentum is always conserved if your system is big enough, if you include all the interacting objects. Well, at first, this ball's moving to the right. Afterward, this ball's moving to the left. I don't care how big the velocities are, that's different. Momentum's a vector. If the momentum's going one way before and a different way after, there has been a change in momentum. So the little ball's momentum changed. It's not conserved. Same goes for the larger ball. The big ball was not moving before, after the bounce, it is going to move to the right. Its momentum changed. It didn't have any momentum to start with, and now it's got some momentum to the right, okay? That leads us to question 7. And I won't put the board up, but the question 7 was, is momentum of the system conserved? The two-ball system, well, the momentum of the two balls combined is conserved because the net force on the system is 0. If you look at just A, when B is hitting A, there's a force acting on A, so A experiences an impulse and a change in momentum. If you look at just B, okay, during the collision, A hits B, so B experiences a net force, therefore there's an impulse acting on B, therefore its momentum changes. But if we look at the entire system, what's the net force on the entire system? Well, we have A hitting B, we have B hitting A. We know via Newton's third law, those two forces are equal and opposite directions, so if the two of them together cancel out. And therefore, the net force on the two-ball system, bouncy ball and beach ball, is 0. So the total momentum of the system is conserved. Now, the way to look at that is the beach ball is going to gain some momentum to the right. The bouncy ball is going to gain momentum to the left. But the total change in momentum is 0. In other words, this ball gives up some of its momentum to this ball, but they exchange momentum. They don't lose or gain it, they exchange it. Now, number 8 is an actual calculation problem. Number 8 says demonstrate that if that V final for the little guy, assuming he's much smaller than the big guy, is about negative V naught backward, okay? And we're going to assume it's a perfectly elastic collision. All right, so now we're going to do a little math. So first of all, we just said that momentum for the system is conserved. So the total momentum before the collision is going to equal the total momentum after. That system, I'm going to assume right is positive, okay? So before the collision, you had little m moving at V naught to the right, so that's positive. Plus, you had big M, but he wasn't moving to start with, so that he had 0 momentum afterward. Afterward, you have little m moving with some V final, which we don't know, which we're going to actually solve for. Plus, you got big M, and I'm just going to say he's moving at some speed V. So I got 3 V's in the problem. I've got V naught of little ball, V final of little ball, and the V final, I'll just call that V of the big beach ball, okay? So I got one equation. Now the problem is I got a whole bunch of unknowns here. I don't know, well, I'll take that back. I've got 2 unknowns. I don't know what VF is. I don't know what V is after the collision. So I need another equation to solve for VF. Well, you do know for perfectly elastic collisions, you know the following relationship. We know that VA minus VB, so the difference in their two velocities before they collide is equal to negative VA minus VB after they've collided. Now, this equation only works for perfectly elastic collisions. This equation is actually mathematically derived from conservation of momentum and conservation of kinetic energy. And kinetic energy is only conserved in perfectly elastic collisions. So please only use this equation for perfectly elastic collisions, which is what we have here, so we can use it. Now we'll put all the actual things in. We'll say A is the little bouncy ball and B is the beach ball. So VA at the beginning was V naught, VB was 0, the big ball wasn't moving before the collision. I'm going to distribute the negative sign in here. So we have negative VA, which is negative V final, okay, and then minus negative becomes plus, and this VB is this V here. So there is our second equation. Now, for the math part of this, what we were asking about was we want to know about VF, okay? So we don't care about V, and I want VF in terms of V naught. So what we're going to do is we're going to solve for V here in this red equation. So we got V equals, if I move this over to here, this becomes V naught plus VF, okay? And then we're going to sub that in right there, and we're going to do a little bit of algebra, and we're going to get V final by itself, okay? So having said that, we end up with mV naught equals, this is 0, I'll skip it, m v final plus big M times, instead of v, we put that in, which is v naught plus vf, okay? We'll distribute the big M, so you got a big M v naught little m v naught equals little m v final plus big M v naught plus big M v final. So I distributed my big M. I want to get the vf by itself. So I'm going to move this over to here. On this side, I'll factor out the v naught. And on this side, I'll factor out the v final. So over here, we're going to have a little m minus a big M v naught. So that's moving this over to here, factoring out the v naught. On this side, I've got this and this left. They're both positive. I factor out the vf. I got little m plus big M vf. And then if you get vf by itself, you get the following expression. You get little m minus big M over little m plus big M v naught. So the question we were set out to answer was, show me that vf is about equal to negative v naught if big M is much bigger than little m. Well, let's check it out. Let's say little m is 1 unit, whatever, 1 gram, 1 ounce, whatever. Let's say big M is 100 units or 100 grams or 100 ounces or whatever, okay? So 1 and 100. 1 minus 100 is negative 99, and 1 plus 100 is 101. Negative 99 over 101 is really close to negative 1. And so you got v final is roughly equal to negative 1 times v naught. V final is roughly equal to negative v naught. So that demonstrates that v final is almost equal to negative v naught. So now you could go back, by the way, if you wanted to solve for v of the volleyball after the collision, which is going to be pretty small, by the way. You could go back and plug all of this in for v final, okay? And if you did that, you would get v naught plus something that's very close to negative v naught, not quite. And so you would get something quite small. Let's do that real quick if you don't bear with me here. So if we get, let's see, I'll do that up here. I'll move this down. Let's see what we get for v of the volleyball. We know it's going to go really slow. When you hit a big ball with something small, the big ball rolls off very slowly. Let's see what we get. So starting with the blue equation there, you get v equals v naught plus, that's v final. So that is little m minus big M over little m plus big M v naught. Okay, I need to get common denominators here to get a fraction. So I'm going to multiply this by little m over big M divided by little m over big M. So I get little m plus big M over little m plus big M v naught, okay? And then plus, and then this, which is little m minus big M over little m plus little m, big M v naught. So I got my common denominators, I can put them all together. So v equals, the denominator will be little m plus big M. How about our numerator? Well, we got little m plus big M plus little m minus big M. Well, the plus big M and minus big M drop out. You get 2 little m's. And then times v naught. So what does this tell us? This tells us, let's go back to our numbers. Let's say little m was 1 and big M was 100. What's the v of the volleyball after the collision? Well, that's 1, so that's 2 times 1 is 2. And that's 1 plus 100, that's 101. So you get 2 over 101 times v naught, which is just under 2% of v naught. So quite small, but quite small. So I hope that problem was helpful, and especially focus on the conceptual questions. Those are the most important thing. What's the same for each ball? What's different? Okay. I hope that was helpful, and thank you very much.